I'd like to talk about two things. One, medicine has been profoundly changed by two fundamental concepts. The idea that systems approaches, systems biology can be focused on disease has led to systems medicine, and the hypothesis that healthcare should be preventive, predictive, personalized, and participatory. We call that P4 health. The other thing that it's led to is that really medicine isn't just about disease, it's about wellness as well. And in fact, we've defined scientific wellness, and I'm going to show you how scientific wellness is not only the key to optimizing individual health, it's going to be the key to understanding disease as well. Now, on this conventional slide of conflict of interest, I'd like to make the point that startup companies have played an utterly critical role, one, in democratizing the technologies we've made, but two, enabling and furthering the visions of biology and medicine that we've had. And in turn, I'll talk about each of those companies as we go through it. I went to Caltech as an assistant professor in 1970 and was incredibly impressed with the complexity of both biology and disease. It was clear that at that time we didn't have technologies, we didn't have a conceptual framework for thinking about all of this complexity. And indeed, it was very much as the famous parable of the elephant and six blind men, each feeling a different part of the elephant and declaring it's a spear, or it's a stump, or it's a fan. And so too was that of biological systems, because we had very few measurements we could make to come to understand what the essence of the elephant was. I remember in '73 reading a book that really had a profound impact on me, Thomas Kuhn's Structure of Scientific Revolution, talking about paradigm changes in physics. And he made two central points. One is paradigm changes are hard to come up with because they require thinking outside the box, and most people can't do that. But the other point that was interesting, at the time I didn't understand it at all, paradigm changes are hard to achieve because most scientists are incredibly conservative and they're unwilling to give up what they learned early in their career. I got involved in a series of what I've called 7 paradigm changes, and I have to say, both of those attributes were utterly true for each of the 7 of these. So one, early on at Caltech, I started bringing engineering to biology. In the sense, I developed their 4 instruments and later several other instruments that really set the framework for modern molecular biology and how it was done. And indeed, these instruments, for the first time, made it possible to think about generating rapid data in biology, and hence they opened up the arena for big data and analytics, which we'll talk a fair amount about. One of the instruments, the automated DNA sequencer, got me invited to the first meeting ever held in the spring of 1985 on the Human Genome Project. 12 of us came and were to pronounce on whether it was a good or a bad idea. And I was struck with 2 conclusions we came to. One, the idea that it was going to be technically possible, though difficult. And 2, the observation that we were split 6-6 on whether it was a good or a bad idea, and the 6 against it were phenomenally against it. And it had to do with big science, and big science would destroy small science. The Genome Project, like no other project, has nourished small science, and it's really transformed the whole field. And of course, what was really interesting to me is going down in the community and seeing 80% of the biologists were opposed. And the institute that was most opposed to it was the National Institutes of Health. And in fact, if it hadn't been for DOE, the Genome Project would have been delayed many, many years. What was also interesting about developing the automated sequencer is we failed for the first 3 years until I realized we needed to really seamlessly integrate together engineering, chemistry, computer science, and molecular biology. And when we did that, within 2 months, we had the basic strategy that later worked out for automated DNA sequencing. But what that made me realize is that departments of biology that wanted to be at the leading edge required a cross-disciplinary framework, because leading edge biology should be able to drive the development of relevant technologies, and they in turn the development of analytic tools. And I proposed the first cross-disciplinary department of the president of Caltech at the end of the 80s, and the Division of Biology utterly vetoed it. And I'll leave it to you to guess why they might have vetoed it. But Bill Gates made it possible to go to the University of Washington and set up a department that was the first such department, and its results were spectacular. I won't talk about them, but it just transformed proteomics and genomics and some aspects of cellular analysis and so forth. But what was very interesting is I'd gone to Washington with the intent of building on top of the cross-disciplinary department a center for systems biology. And what was very interesting is systems biology was really different from previous biologies, and an academic bureaucracy just couldn't manage that. To give you a simple example, I said, look, I really need a lot of space for computation. And the head of computing at the University of Washington came over, showed me a really small janitor's room, and he said, you're a biologist that has more than enough room for any computation you'll ever have to do. And that was kind of the attitude. So I did resign in 2000 and start the Institute for Systems Biology. And here, the idea was to look at the elephant and to be able to assess it in a global and comprehensive kind of manner. And I'll give you all sorts of examples of that. And of course, we immediately applied these systems thinking both to biology and to disease. And that brought us to these ideas of systems medicine and the emergence of this proactive P4 healthcare and/or medicine. But in the context of thinking about P4 medicine, what also became obvious was that scientific wellness is an utterly major thrust that heretofore had been utterly and entirely ignored. And the approach we took to dealing with scientific wellness we call dense, dynamic personal data clouds, and I'm going to show you exactly what they are. They are the essence of what precision medicine should be. And the final change happened actually just this last April when my institute affiliated with the Providence healthcare system, a major healthcare system that opened for the first time, bringing the possibilities of P4 medicine directly to the patient's bedside. And I'll show you the kind of things we're going to do. I'll tell you also, I had spent more than 10 years going to 6 top-flight academic medical centers, and I never got anywhere in proposing systems things. And it was all about silos. It was all about people who were threatened by worry that resources would be taken from them. And they're paralyzed in many ways in really doing innovative things. And you know, my most fundamental philosophy is new ideas need new organizational structures. Almost never can an old structure really handle a new idea effectively. And that's true of skunkworks and industry, a very interesting conversation we could talk about. Now, here are the 6 instruments that we were involved in developing. And in the red are the companies that we started in order to be able to create those instruments. It required actually 3 different companies to do the 6 different instruments and so forth. And again, this idea that government funding can't do a lot of things we need done, so we should be fearless in looking for resources in other kinds of directions. Now, systems thinking brought 2 things to systems medicine. One, this idea of dense, dynamic, personalized data clouds, data of all different types, kind of a 360-degree survey of the individual. And the idea with these data clouds is that we can, and they included billions of data points, we can actually integrate these data, and they will lead us to actionable possibilities that let us either improve wellness or avoid disease. And we'll show you some nice examples of that a little later on. This actually turned out to be the essence of what I would argue precision medicine should be in the future. Now, one of the things we can do with these dense dynamic data clouds is we can define the nature of the biological networks. Biological networks are hierarchical. They can operate at the chromosomal level, at the molecular level, at the cellular level, at the level of organs, at the level of individuals even. And what the essence of them is they govern the information that regulate development, physiology, and the aging process. If they become disease-perturbed, they cause disease. If you can figure out the key disease-perturbed networks and how their structures have changed, you gain fundamental insights into the pathophysiology of disease and powerful new approaches to diagnostic and drug markers, and we'll show you some examples of that in just a few moments. So by 2006, we were in good shape. We'd clearly defined systems medicine and P4 medicine, but in many ways, we were exactly at the point we were with the elephant when we were thinking about, in the early 70s, biology and what it was about. And what we needed were a whole series of technologies and systems-driven strategies to be developed. And what was utterly clear is NIH was not interested in funding any of those unless you could more than prove that they were going to work. And of course, if you take high-risk things, there's no way you can prove they're going to work before you do them. And of course, to do them does require money. So one of the most fortunate experiences of my life then occurred in 2007 when I met the Minister of Finance for the state of Luxembourg, who was the most powerful politician in Luxembourg, and had decided he was going to transform their economy from a 90% dependence on financial services and bring in biotech and healthcare. So he asked us to write a proposal over a 5-year period to help them do that. We did so, and we actually set up an institute very similar to our own at the newly minted University of Luxembourg. It's one of the most spectacularly successful systems biology institutes in the EU today. And we did a lot of other things I won't talk about. But what they did for us was to give us $100 million over a period of 5 years to invent the technologies and strategies of systems medicine. And so in 2012 and 2014, I really began thinking about what we needed to do to create a P4 healthcare system. And the idea that we came up with is that we would take 100,000 normal individuals, we would use dense, dynamic, personalized data clouds, and we'd learn about wellness and about disease transitions and about disease. And in fact, in 2014, we started 108 friends on that project for a year, and I'll describe the results. They're absolutely spectacular. What was interesting, of course, is this, again, is the essence of what precision medicine should be. It was a year later when Obama, in his State of the Union address, first proposed the Precision Medicine Initiative. And I'll tell you, I went to NIH at the beginning of 2014 and asked Francis Collins whether they would be willing to support this wellness kind of program. And he said, no way. NIH will never be interested in scientific wellness. And, well, I'll leave it at that. So, and finally, as I said, we did affiliate with Providence, and that has opened up really incredible opportunities that we'll talk about. So let me talk a little bit more about these technologies, and you all know about tipping points. It's the magic moment when an idea, a trend, a social behavior crosses the threshold, tips and spreads like wildfire. And of course, what's interesting about tipping points is they have different trajectories. There is the origin of it, there is the tipping point at the edge, and it's spreading like wildfire. And we'll show you all examples of those kind of things. So Luxembourg catalyzed about 10 technologies and systems-driven strategies. And for the most part, I'll talk very quickly about these. Third-generation sequencing is the analysis of single strands, very long single strands of DNA, using electronic detection and nanopore or nanochannel strategies. And my prediction is that within a 5 to 8 year period, we'll have human genomes that can be generated in 15 minutes and will cost of the order of $100. Absolutely straightforward. What it depends on is whether we can get venture capitalists, investment bankers to invest in third-generation sequencing. The first two companies failed disastrously, so everyone has been reluctant. Diagnostic microfluidics and nanotechnology. I'm going to show you a spectacular example of this in just a few moments. I've got a good friend at Caltech and collaborated many years with him on using small circular peptides to create protein capture agents that have enormous specificity and sensitivity, have very little cross-reactivity, and can be used either as diagnostics or therapeutics. I think they'll replace monoclonal antibodies in a period of time. I'll show you where we're going to use these things. We've cross-linked both big molecular machines to understand their structure, and we've cross-linked networks to understand their organization and so forth. We've used mass spectrometry both in a global and in a highly targeted sense. Our biomarker, blood biomarkers come from targeted mass spectrometry, where we can look at 100 proteins at atomole level sensitivity. And I think one of the areas that's going to be most transformational for understanding the complexity of biology is single-cell analysis. And I'd love to be able to tell you about some of the things we're doing, but we don't really have time. Systems-driven strategies are those where you take one or more technologies, you create a platform, and you weld together the computational wherewithal that are required. Family genome sequencing, where you sequence families, gives you the ability to identify genes and classic Mendelian traits, single gene kind of traits. But recently we've studied 42 families that have multiple affecteds with bipolar and compared them with a control group, and the data are spectacular. We found 125 genes clearly causative. Each individual had 3 to 4 of those genes. All of those genes fell into just one of two functional categories, related to GABA receptors or related to calcium ion channels. So what this means is we're going to run into a lot of very complex diseases in the future that are going to require us to transform how we think about attacking them. And systems approaches are the only way we'll be able to do it. The next 3 things I'm going to talk about, and the last thing that I'd love to talk about is the work from a fellow in Montreal, Mike Tyers, who is using natural synthetic products to be able to create drug libraries of 1 billion different entities that can be screened incredibly rapidly. And I can give you all the details, but it's going to transform drug discovery, and it is the only solution to these highly resistant bacterial infections. The only way you're going to deal with them is on-site, create a new drug that can deal with the new one. And we can do this with this kind of technology. But I'm going to take a few slides now and show you in a mouse model of neurodegeneration how we can study a disease from the beginning to the end, how we can delineate the biological networks that become disease-perturbed in their proper order, and how we can actually follow those changes in the brain, in the blood. And we can apply all of these things to human beings. It's incredibly exciting. So the disease is injecting activated prion particles into mouse brains, and it creates a disease that runs over 22 weeks or so. And then we looked at the brain transcriptomes, the messenger RNA in the brains, at 10 times across that time period, subtracting at each of those time periods the transcriptomes of the normal mice, so we only looked at the genes that activity changed. And we came to the conclusion 300 genes were involved in this process. And we were able, through histopathologic dynamic analyses, to define 4 major networks that seem to mediate this entire process. And each of those 4 networks showed different types of dynamics across the 22 weeks of the disease. The red indicates changes here. But the really important points are 2. One, the 10 networks that we defined and their dynamics explain virtually every aspect of the pathophysiology of this disease. And 2, those networks were sequentially disease-perturbed, starting first with the network that was the most unique to the disease, one called prion replication and accumulation. Now, why is that important? It's important because if we look at that first network and use the tools of systems biology, we can begin to get diagnostic reagents and therapeutic reagents that would reverse that network. So the idea is 11 or 12 weeks before you ever see any signs, we reverse the disease. And I'm going to show you later how we can do this routinely in the future in humans. And in fact, the preventive disease of the 21st century is going to get to identify the earliest disease transitions and reverse them. And we'll give examples of what we think we can do. How did we actually analyze the blood? We learned that by comparative analyses of the messenger RNAs in all 50 human organs, and we did it for the mouse as well, there were transcripts that were uniquely present in the brain. And we were able to discover close to 100 of those transcripts that made proteins that were present in the blood that we could detect with mass spectrometry. So if you had 100 of these things in a normal animal, they'd all be set at different levels in the blood, okay? And if the animal became diseased, those networks that became diseased would change the concentration of their cognate proteins. So you could distinguish health from disease, and if disease, because each disease uses a different combination network, we could distinguish the diseases. We took 11 mouse brain-specific proteins that mapped into each of the 4 major networks, and we showed beautifully in the blood we could see the same transitions we'd seen in the brain. So you don't have to think about assaying brains, you just have to think about assaying bloods. And one of the really cool ideas is, let's suppose we could get 50 organ-specific proteins for each of your 50 major organs. Wouldn't it be cool if we could set up a microfluidic ELISA assay and conceptually We know how to do this except for one thing, and that's make lots of these protein capture agents. And I told you how we're going to do that in the future. But what we could do with a drop of blood and analyzing that every 6 months is we'd have an assay of every single major organ, and we could see the earliest transitions from wellness to disease. So you truly would have a tricorder that's not based on a very limited number of parameters, but it's looking really at everything. How do we make blood a window into wellness and disease? We set up the company called Integrated Diagnostics and really pushed this idea forward, and it was absolutely a fascinating problem. So in lung cancer, there are in the US today 3 million lung nodules. The pulmonary oncologists must say, gee, what do I do with that? 600,000 of them go to surgical procedures that are expensive. More than 50% of them, the procedures are done on benign nodules. So you waste money and you waste morbidity. So we set out to get a marker that could distinguish benign from neoplastic nodules. And I'm not going to go into the details, but we started with about 400 blood proteins that we chose. And through a series of systems-driven filters, we drove it first down to 13, and more recently down to just 2 proteins, so we can put together a very simple ELISA assay. And those 2 proteins let us identify at the 95% level more than 50% of the benign nodules. We can take those people out, put them in watchful waiting. We eliminate 40% of the unnecessary surgeries. And the reason 4 major insurance companies have agreed to pay for this is because that saves the healthcare system about $4.5 billion a year. So if you're clever about what you do, you can persuade even reluctant payers to buy in. The 12 out of 13, or both of the 2, all map into disease-perturbed networks in the brain. So the filtering gave us biology as well as terrific kinds of biomarkers. And we've done that for preterm birth now. We have a 2-marker preterm birth diagnostic that can operate at 19 weeks with incredible efficiency and warn you about who are the candidates. And of course, you can give them progesterone. You can delay the pregnancy, and that matures the baby. So you avoid a lot of the enormous expense of this disease. We've actually done it also in a very preliminary way for post-traumatic stress disorder. So we can beautifully distinguish Afghanistan soldiers that came back with PTSD from those that did not. And the real importance of this, and it's at the beginning, but it is a disease that heretofore had only been diagnosed by psychiatric methods. And we've proven that for psychiatric diseases, we'll be able to quantify them in the future. And I think this will apply for many different diseases. And we've done it for a tumor as well. This is my favorite Freeman Dyson quote: "New directions are launched by new tools much more often than by new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have yet to be explained." And the Genome Project was a wonderful example of that. So we've, in 13-14, had a convergence of systems medicine and this digital revolution. You're spending a lot of time talking about big data and its analytics and social networks. And what that let us do in considerable detail is refine our understanding of P4 medicine. And what I want to do in the next slide is show you how dramatically different it is from contemporary medicine. 1, it's proactive, not reactive. 2, it's all about individuals and not about populations of individuals. 3, it's about wellness and disease, not just disease. And 4, it's about generating these dense dynamic data clouds. And the reason that is so important is it's the only way we can capture across time for each individual the blending of your genetics with your environment. And that's why I've always hated genome medicine as a term. Genome medicine is one-dimensional. We really should be wanting systems medicine. So, but the other thing it says is the way we generate drugs today is fatally flawed. So the idea is you have 20,000 patients and you give them a cancer drug or placebo and you extract the data out. But then you ask yourself the question, aren't each of these individuals different genetically and environmentally? And if they are, you can't average very different individuals. And what you do is you enormously enhance the noise. And of course, Big Pharma has been more than capable at proving that. So what P4 medicine does is we'll have 20,000 individuals, each with their own data clouds, and we'll stratify them according to the properties we're interested in, and those stratifications will come from the essence of what they are. Do you respond to the drug? Do you not? And all the other things that we might want to do. And I'll tell you in the future, N of 1 experiments are going to be the only way to deconvolute enormous complexity in disease that conventional clinical trials couldn't even begin to approach. I don't even think people have thought very much about it. But patient-activated social networks are great for teaching patients, probably for physicians, healthcare workers as well, crowdsourcing, advocacy, all the things that we know and love. And I think this is the most dramatic slide you'll see in my talk. So the orange people are the responders to the 10 most common drugs sold in the US today. And you'll see that the responders vary from 1 in 4 to 1 in 25. The vast majority of people given the drugs are exposed to their cross-reactivities, exposed to their cost. They get nothing out of them. The way we do clinical trials now, you have no chance of being able to identify the orange from the non-responders. If you do it the way we've proposed with P4 medicine, you'll instantly be able to segregate the responders and analyze them and characterize with biomarkers their difference. And what's really cool about that is Genentech has demonstrated if you can go to the FDA with 40 patients and 39 of them succeeded, you'll get your application. They did that basically with Herceptin. So with the stratification we can do, it could just change the cost of drugs in the future. So there are 2 different dimensions to healthcare. One is quantifying wellness, and the other is disease demystified. And our argument is that scientific wellness, which I'll define for you in just a moment, is going to create an industry in contrast to the disease industry or the current healthcare industry that I think will, in a period of 10 to 15 years, exceed in market cap the disease industry. And what I would say is today, 98% of the resources go into disease, and that's exactly the wrong way to do it. 98 should be going into wellness. Not 98, but a large amount should go into wellness. And that's the shift that will occur in the next 10 to 15 years. But what I'd really like to emphasize now is the enormous power of this platform we call dense, dynamic, personalized data cloud. So one, it gives us the means to optimize wellness, and I'll show you a little bit about what that is in just a moment. But most important, if we take large numbers of individuals and follow them for an extended time, we'll start to see transitions into every single common disease. And we'll be able to use the approaches of systems biology to identify them and reverse them. And that is going to be the preventive medicine of the 21st century. You'll have your diseases reversed before you even have the faintest symptom, just like the mouse in the brain that we talked about. And of course, the third area that's really going to be key is we can use these clouds to follow individuals with disease, both progression, response to therapy, and what happens after that. And this gives us the ability to look at disease in a dimensionality that is utterly unapproached by anything anyone else can do today. And the N of 1 experiments. Too bad we don't have time to talk about that. That's a great thing to think about. Why is wellness so important? You can make a calculation that half the kids born in this calendar year are going to live to be 100. And the key question is, what's the quality of their life for the last 35 years? Scientific wellness is absolutely going to transform that. And another statistic that really is interesting, several studies have done this, determinants of health in the US. And the observation they've come to is your genetics contribute 30%, your environment and lifestyle contribute 60%, and the healthcare system contributes 10%. So what we want to do in scientific wellness is we want to capture that 90% and really focus on that. So how are we going to do that? We're going to do it by setting up this 108-person wellness project in 2014, abbreviated HPWP. And we're going to use these dense dynamic clouds. And this was an IRB-approved study, so it let us do a lot of nice things we couldn't otherwise have done. What is a dense dynamic data cloud in this particular instance? It is your complete genome sequence. It's generating blood samples every 3 months, so we can measure clinical chemistries, metabolites, and selected proteins. It's taking samples of stool every 3 months, so we can look at your microbiome. And then it's using quantized self-measurements with a Fitbit to determine activity, quality of sleep, pulse, and things like that. So the idea was that every 3 months we would take these samples, and that every month we had coaches that would then look at these data and integrate and model them and bring back the actionable possibilities that, again, could increase wellness or let you avoid disease. And what is utterly essential, and this is really key that you understand it, what made this possible were coaches that would bring the actionable possibilities to each of the pioneers, would tell them in simple terms what the actionable possibility was, but more important, would place it in the context of their own healthcare objectives. These coaches were able to get 70% compliance with actionable possibilities. And when we started this study, I would have thought we would be lucky to get 10%. So I can tell you unequivocally, no app is ever going to replace a coach. An app can enormously amplify what a coach can do, but it's not going to replace a coach. And the data are absolutely spectacular. I love this analogy, just like the Hubble telescope gave us the ability to look at the stars with a resolution we'd never had before, so these dense dynamic data clouds have let us look at aspects of human biology and human disease in ways we could never do before. And we've, in the first analysis, there were really 3 striking kinds of conclusions we came to. One, we were able to identify 4,000 correlations between the various types of data that we had. I'm going to talk a little bit about each of these. But number 2, we could actually use your genome sequence data in the context of genome-wide association studies for 60 or 70 different diseases, and we could give you your risk for these diseases. And we proved that these estimates were actually accurate, and I'll show you that in just a second. But the other thing that's really cool is we can obviously see state transitions between wellness and disease and so forth, and we can use those in an incredible way. So there are 3 dramatic things that we've never been able to do before. Here is the latest correlation network, or really a small subset of it. There are 6 major data types, and we asked for a bit in one data type. whether there were correlations with any data bits and any of the other 5 data types, and got more than 4,000 of these correlations. And I'm going to show you how we study these things, but they gave us insights into new drugs. They gave us insights into new biomarkers. They gave us insights into systems that were connected. We had no idea were connected before, and on and on. There is an incredible mine of IP, and we haven't quite even figured out how to be able to deal with it effectively. So one of the things we did is take the first statistical interaction network, which looks like a hairball, and then we applied to it an algorithm that said, throw out the probabilities that are the lowest. And as you threw out the probabilities that were lowest, you began to see discrete domains within the network. And those domains, interestingly enough, represent physiologies and represent diseases that are absolutely fascinating. And in fact, we took one, the cardiometabolic domain, and we were able to say there was a protein that correlated in really interesting ways with that domain, and lo and behold, it's being developed as a drug by Eli Lilly. And we've done that with a whole series of other things, but we have far more possibilities that aren't drugs yet and are real opportunities to develop them as drugs. So we can determine your genetic risk for 60 diseases. We add up all the little variants because they're basically probabilities. And what that gives us is the ability to take the 108 individuals and bin them into 5 categories from low risk to very high risk. And what we have in 5 different diseases now done is shown the genetic binning of the 108 pioneers correlates beautifully with the disease phenotype of the corresponding disease. So there is an identity that allows you to do interesting things. And even more impressive, since we have 2,000 normal genomes at ISB, we can do the genetic analysis for a given disease for those, and often we get bell-shaped curves. So we can put then the pioneers on those bell-shaped curves, and you have relative risks given your dominant population and so forth. And we'll talk later about all the different kinds of things you can do. Here are a list of the diseases we can do this for. Many of them aren't actionable. But if we do this for you, we can, number one, tell you when they become actionable, you ought to be aware of this. Number two, we can follow particularly carefully with the dense dynamic data clouds and go to you, say to you, you've started to transition. Whatever we can do, we better get you working on things. And three, what is really cool is, and we're going to do this with Alzheimer's disease, is we can take the highest risk individuals and we can put them into clinical trials looking at drugs that will attack the earliest stage of the disease, and we can see just how they behave and perform. And we'll talk more about that later on. So the state transitions from wellness to greater wellness. We saw that in many of the individuals, and that provides us then with metrics that are going to allow us to create absolute metrics both for wellness, physiologically and psychologically, and we can talk more about that. Wellness to less wellness is the inverse, the wellness to disease transitions, the preventive medicine of the future, and then following disease progression and so forth. And of course, the most powerful incentive for the 108 pioneers was to see their chemistries change as they followed the actionable possibilities. It really hooked all of us in various ways. Here's the first clinical chemistry we looked at. These are well people. 90% had nutritional abnormalities, 70% inflammatory, 60% cardiac, and 55% diabetes. And what I will say about these, over time, things improved. So here's cardiovascular. It didn't improve much. Here's diabetes. It improved strikingly. Inflammation was better, but not ideal, and nutrition was okay. The whole point is, you're never going to change a lot of these things very quickly, and you have to work at it, and you can't expect to change them. And I'm going to make the point later that wellness should be a lifelong journey. You don't do it for a year and figure you're cured or anything. With your genetics, we can tell you how you should diet most efficiently. With your genetics, we can tell you how you can exercise most efficiently. There are 330 variants that predispose to athletic injuries. If you know you have them, almost all have exercises that will let you avoid those things. And heavy metal toxicity, we had 3 people that had blazingly high levels of mercury. 2 of them ate excessive amounts of tuna sushi. And when we substituted salmon for tuna sushi, their levels came right down. And the third had amalgam fillings. When he got rid of those, his level came right down. So the pioneer insights, one was we can control and make our own decisions if we have enough information. The second was your genes don't need to be your destiny. They kind of control your limits. There are many ways you can get around these things. In not all cases, but in many cases. And I think the most important thing was these people came in arrogantly assuming that they were healthy, and I think most of them, frankly, found that they maybe were in the lower 25% of wellness, and they went up many, many levels across the course of the year. This is the group we put together to do this, and we transferred it virtually intact into a company called Aerovale that was focused on a consumer scientific wellness company. And ISB and Providence are going to use the dense dynamic data clouds. We're going to get the wellness metrics. We're going to develop better assays, so the cost of this will come down, hopefully very quickly, and better analytic tools, and use these dense dynamic data clouds in all the way that we've talked about before. Aerovale is started in June or so of last year. It has 1,200 customers. I think it's been just absolutely a smashing success. And we're just opening up shop here in California. It gives the pioneers, that's what we call them, 6 different dimensions of health: heart and diabetes and inflammation, nutrition, healthy aging, and stress. And the idea is, just as I said before, that you get a dashboard that regularly shows you just where you are, and you have these regular coaching calls that discuss the priority of your actionable possibilities, because everybody has many actionable possibilities. We have a terrific scientific advisory board. I will talk about them. So let me close then by showing how that Providence, in its affiliation with ISB, is going to really change the world of medicine. So one, we are the research arm now of Providence, that is, ISB is, and I'm Chief Science Officer of Providence, and I do have a lot of influence in the kind of things that we do. Providence is in 7 states, 50 hospitals, enormous numbers of patients. It's a $20 billion a year operation. So it has enormous resources that we can mine, 30 million electronic medical records, and we're already starting to think of the many things that we can do for that. So let me tell you about the 4 translational pillars that we're going to be bringing to Providence. The first is scientific wellness, and the idea here is to take 2,000 of their employees, 2,000 control employees, to run the study for 3 to 4 years and be able to ascertain the increased wellness on the scientific wellness group and how much money they save the healthcare system. And I'll guarantee it's going to be an enormous amount. And this is the way to bring payers, obviously, into the picture. We're taking 200 women that have been newly diagnosed with breast cancer. We're going to follow them all the way through surgery, radiation, chemotherapy, whatever it is. And then we're going to do our best, especially aiming at the 10 worst complications of post-breast cancer disease, to bring them back to wellness as quickly as we can. And this would work for any type of cancer that you'd want to talk about. We're going to attack Alzheimer's disease in two really interesting ways. A collaborator of ours, Dale Breseden, has developed a 36-bit regimen where he's successfully shown in 100 or so people that he can transition them from the earliest stage of Alzheimer's back to normal and keep them there as long as they stay on the regimen, okay? So what we want to do is exactly the same thing, only we'll have controls and show just how effective it's going to be. So I think we're going to be able to reverse the earliest stages of Alzheimer's, and we'll use the dense dynamic data clouds to get very powerful early diagnostics so we know unequivocally as soon as you start to transition into it. The second thing we're going to do is we're going to take 200 people that have the highest risk for Alzheimer's, we're going to put them on the dense dynamic data clouds. The second they start to change in a bad way, we'll put them on the Breseden regimen. So we think we'll be able to take high-risk individuals and keep them from ever getting the disease. And if all this works, it'll be wonderful. And the final thing we're going to do with glioblastoma, we're going to do many things, but the one thing I'm really excited about is I've always thought cancer was a disease that's exactly like AIDS, and the only way you're going to cure cancer is start with triple drug therapy on day one. This idea of giving you one drug at a time is a disaster. So we have all sorts of techniques for getting high throughput analyses of the cancer tumor stem cells. We can easily get those cells from glioblastomas. And we think within a 2 or 3 year period, we'll really prove this hypothesis that triple drug therapy is really going to be the way to go. So finally, we are going to bring P4 medicine to the healthcare system. We are going to use these dense, dynamic, personalized data clouds to assess your environment and your genetics and assess just what we need to do to optimize wellness. We are going to be able to identify the earliest transitions, reverse them, and create a new kind of preventive medicine in the 21st century. And scientific wellness being a lifetime journey. So bear with me just for 1 second to tell you why I think this is true. Number one, AirVale, as time passes, generates many more actionable possibilities, and that's going to go on indefinitely. Number two, Eric Topol has studied a group of 1,000 people called the elderly. These are 90-year-olds that have never been sick a day in their life, never taken a drug, fully mentally capable and healthy. And number three, when we did a study of people 115 or older, 18 of them, about 6 or 7 years ago, and that never worked because we didn't have the power to make any conclusions. But what I did learn is if you can get to 100, almost everyone dies very quickly of a sudden systems failure. So my hypothesis is that if you participate in scientific wellness for your entire life, aspiring to all the actionable possibilities, we can elevate you to the status of the elderly, and we can bring you into the 90s mentally and physically functional. And of course, when you get to be 100, you're really on your own. So, okay, I think we'll reduce healthcare costs. I think we're going to create a new wellness industry. Every one of those pillars is a wonderful potential company if you think about it. The data are going to transform the life science endeavor. And my real hope is through the assays cost $6,000 per person per year. I'd like to see that be $100 in 8 years, 10 years. And then I'd like to take this to the developing countries of the world and have this enormous excitement of efficiently bringing them in to the kind of opportunities we've talked about here. That is, a democratization of healthcare that was inconceivable even 5 years ago. Thank you.
Thanks. Oh, thank you.
Yeah, yeah.
So you're true to force and a true pioneer and visionary here. Two quick questions before we go off to dinner. What have you learned as a pioneer yourself using this data? And what's the biggest barrier to getting this to translate to reality across healthcare?
So I was one of the pioneers, and my major health goal was to be able to get back to my college football playing weight. And I was 20 pounds above that. And in the first year, I lost 15 pounds. And it made an unbelievable difference in how I felt. And I must say, as I go around now and look at people, I think to myself, goodness, couldn't we get them in the program and make them healthier and happier? The second major, really interesting thing that I learned is 90 of the pioneers had low vitamin D levels, and I had a really low vitamin D level. And so they put me on 1,000 international units of vitamin D. Didn't absolutely touch it at all. And then we realized that there are 6 variants and 3 genes that block the uptake of vitamin D. If you have 2 or more of those variants, you need megadoses of vitamin D even to begin to get up to normal levels. So I take 10,000 international units a day now, and I'm just barely nudging the bottom end of normal. So what really is interesting is we all have nutritional shortcomings. Look, you're young, healthy, and immortal. You're not going to think about it. They do make a difference when you get older. And that's part of what AirVale is an investment in optimizing your future wellness. That's really going to be key. Great. And your second question was...
Very quickly, the biggest barrier you see between getting this to really being enabled?
Look, the biggest barrier is the cost of the assays. We have to bring them down. And we know how to do that. That's one of the reasons I was so disappointed at what happened to Theranos. I really think they're really on the right track, but they got the wrong personality running the show, unfortunately. But I think it's going to be microfluidics and nanotechnology, and we're going to be doing all the assays from a drop of blood kind of thing.
Let's thank Lee also for all his amazing contributions to science and medicine.
Mm-hmm. Okay.